So hello everyone and welcome to today's Geoactive webinar. And today we're going to be talking about the latest developments in IP's Experienced Eye module. And that's a module for feature selection and machine learning model prediction. And we can view the results in a very nice and interactive way. So we'll see what we've got new in the latest version. So what we're going to do is just cover an overview of feature selection, and then an overview of what Experienced Eye is if you've not come across the module yet within IP, and then we'll go through some of the changes that we've made in our latest update, update 3. And then we'll jump on to a live demo and then take any questions at the end. Okay, so machine learning is increasing in popularity within sort of all domains these days, especially with AI and large language models. But within the geoscience domain, it has many benefits, including automating the petrophysical workflow or the interpretation workflow, as well as improving any predictions that we make, say for permeability, porosity, or missing curves, missing data, and it can be very powerful, but there's a lot to machine learning these days and a lot of moving parts to it. And when we look at machine learning as a whole, this is just a very simple workflow through machine learning. And what we start with is the project definition, and that's where we define what we're wanting to do, what are the business goals, for example, or what are the project goals. So we may want to predict rock types, we may want to predict missing data or predict continuous permeability from discrete core measurements. So right at the start, we need to understand what it is that we are wanting to do before we start moving on to the next stages. And those next stages are about data collection. So we gather up all of our available data, and that can include well logs, core measurements, gas data, mud log data, anything that's related to the well and what we're trying to do. So when we've got that data, what we tend to do is split it out. And we split it out into our testing data. And that data is set aside so that we can validate how well our model is performing. And then we can see how well our model generalizes to new data. The rest of the data is put into modeling data, and this is where we start to carry out EDA, which is exploratory data analysis. We start to look for patterns within the data. We try to understand the data, the relationships between all the different input curves, and we also carry out data QC, which is a step that should never really be missed when even doing a simple petrophysical interpretation. It's a very important step. If you start to have issues in your data very early on, and you carry them all the way through to the end of the machine learning model process, then those errors can be amplified or go unnoticed and then cause issues further down the line for whoever's going to work with that data or make business decisions from that data. The data QC and data repair stages is probably one of the most important parts of the workflow before even getting it into machine learning. After that, we try to identify what are our most relevant features, what features out of this data set of, say, 20, 30, 40 logging curves and different measurements, what ones are going to be the most important. And we'll see why that is important in the next slide. Once we've identified the key features, we can then take our prepared data and then split it again. And this is where we split the data into a training set, which is used for modeling the data and or performing the machine learning model and training the algorithm on that data to come up with its best guess at how it can use that data to predict new data from it. The validation data set is then set aside, and that is used to evaluate the model on how well it performs, but it also allows us to tune any parameters within the model, tune our data. So we may end up going back and maybe adding in an extra curve, or we find that we need to bring in more logging measurements from our main data set. And it just helps us to tune that model so that we can get the best model possible. And then we evaluate the final model on that test data that we set aside very early on. And that allows us to understand how well the model generalizes to new data, whether our model is just memorizing patterns within the data, which we don't generally want to do. We want it to be able to make a prediction on new data, and that prediction be reasonable or as accurate as possible. Once we've done that evaluation, we then deploy the model and then we monitor it for any feedback, any issues, and any data that we say acquire. Say we've got 5 wells in our model, and then we acquire 2 new wells, and then we say in one of those wells there's new geology, which that's not present within the other wells, say a carbonate interval, then we need to take that into consideration and go back to the process of retraining our model and trying to get better predictions with that. So feature selection is the place that we have focused on, as well as that machine learning training and validation workflow. That's what we've focused on with Experienced Eye. And for those that are not familiar with feature selection, but basically it's the process of identifying and selecting the most relevant features from a data set. And that allows us to build more efficient models and more robust models, as well as making models more interpretable, which is a key thing. If you start feeding data into a model and you don't understand what's happening, and then you get an answer out, you've lost that connection between the input data and the output data. So with feature selection, you have an idea of what inputs are being used to drive the model and which ones are the most relevant in getting to that final result. So there's a bit of terminology here when dealing with machine learning and dealing with our domain, the petrophysics, geoscience domain, and that is that in machine learning, the individual variables are called features, but in our domain, we generally call them well logging curves or well log inputs. So these terms can be used interchangeably, but they generally mean the same thing: features, well logging curves, and variables. Why is feature selection important? Feature selection is important as it can help reduce the training times of our models. So there's less input data to train our models, and we can get results faster. We can also improve interpretability. We then have less features that help us understand our output from the model, and we also reduce the chance of overfitting, and that means that the data has less chance of memorizing the training data. So when we try to apply it to new data, then we want to try to get the best model possible without having to change our model and without the issues of overfitting or memorization. And we can also improve prediction accuracy. So feeding in every possible input curve does not mean that we will end up with a better model. So we want to try and subset that down to the most relevant features. And that ties in with the first point, where we have less input data, we can then reduce those training times of the models. So just as an example from petrophysics, here we've got a target curve of porosity, and we're trying to find out which curves are the most relevant. Could be a case of trial and error. We may be trying gamma and density and neutron and compressional, which are all tied in with porosity. And then some of the other curves might be less relevant. Maybe caliper is a lot less relevant to porosity compared to density. So we can use our domain expertise, but there may be cases where there are unseen relationships between the data, and that's kind of what these feature selection models try to identify, some of the underlying relationships. But at all points within the workflow, you are in charge. You can say, well, why is this model picked caliper? Well, we don't really need it, but you can try and understand why it was picked, or look at the charts and cross plots, etc., to see what's the relationship. Has it picked something up? Has it picked up noise? Or is there a difference in, say, washout and more solid hole? Then there might be some relationship there. Just to give an example where we have 14 logging curves. So this was an example from one of our papers that we published a few years ago on Experienced Eye. And here we have a set of 14 logging curves, and we want to know which ones will be the most relevant to predicting porosity. So one feature selection technique we can use is the Pearson's correlation, which is a filter-based method and is used for measuring the strength or the relationship, so the strength of the relationship between two variables. So the value can range from -1 to +1, and values that are close to -1 or +1 indicate a strong relationship, whether it's positive or negative, and values that are closer to 0 indicate that there's no relationship. So as part of this study, we converted the Pearson's correlation to absolute values and incremented it in 0.1 intervals, so from 0.1 all the way up to 0.7. So we ran the model multiple times to see which features would be dropped out and what the impact is on the actual prediction. So when we start with all 14, we can see that we've got quite a scattered result on the right, which is our actual porosity versus predicted porosity. And we can also see the metrics are relatively poor. As we increase that Pearson's correlation cutoff, we then start to drop some of the features that are poorly correlated. So in this case, we've dropped C1, C4 ratio and our delta rho curve. And we can see that the model has worsened in performance. It's more spread out. But as we start to go through the iterations, we start to improve the performance again of the actual versus predicted until we reach the final iteration where we have 3 features left. So bulk density, acoustic compressional, and our total gas, or our average gas, I think this one was. And this indicates that these 3 features would produce the best prediction result, and we can see that on the scatter plot where we've got a tighter correlation in the lower porosity intervals, say below 0.15 for our porosity. And in the upper intervals, we've still got a little bit more spread, which we may be able to explain with maybe another input curve, or there may be something that requires further investigation. So the gas here might have been included because there might be a light hydrocarbon effect on the porosity, and that's what we're picking up, or what the gas X is picking up. So that's why that's possibly been included. So what is the challenge? Well, the challenge is that this is a manual process, or it was a manual process, and can require multiple iterations to find the best combinations of inputs. So you're taking your inputs and you're running them through a machine learning model. Okay, maybe that one doesn't work. And then you go back and you change the inputs again and see how it performs. And that is sort of an iterative process, but it's very, very time consuming. To give you an example, if we start with 3 different feature selection methods, say Pearson's correlation, backward feature elimination, and experienced eye feature selection, then we can run that through 3 different machine learning models. That means that we've got 9 separate runs to run through that process of going from our data, selecting the features, running the machine learning model, and then evaluating the performance. But if we start to bring in the aspect of different groups of input curves, such as the top 3 to top 8 ranked features, which we'll see in Experienced Eye, then that can rack up to about 54 separate runs. And you can imagine how long that might take you to do, sort of going through the process from start to finish, and that can take several hours to days, depending on how quick you move with adding the curves and moving the mouse around. So that can vary as well. So, but the main thing here is it can be a slow and tedious and manual process, and that's where we developed Experienced Eye. And Experienced Eye was brought in to IP in version 2023, and it was basically a new module that's been developed from the ground up. And this allows us to bring in interactive results to the grid to visualize model performance. And it also automates and streamlines the process for curve prediction. So we take our inputs We select our models, we select our feature selection models as well, and then we run that, and then it can be done in several minutes to do that. But when we implemented this in 2023, and it was a single well module, so we were running on a very small data set. And what we've done since then is, okay, so before we get on to what we've done on the upgrades, just to give you an overview of what's actually happening behind the scenes with Experienced Eye. So we basically take the input curves, we carry out some data quality checks on that, and then using the feature selection models, so Pearson's correlation, backward feature elimination, and Experienced Eye feature selection, we try to obtain the top 3 to the top 8 ranked features for each of those methods. And we also have a user selection, so you can have a preferred order for your inputs. So if you want to see how well your say domain knowledge compares against the machine, you can set the order of the inputs and see how that performs relative to the automated methods. And then each of those grouped rankings are then passed into the machine learning model, and then we evaluate the performance with some standard metrics. Now, I should point out that this whole Experienced Eye module is currently focused on regression problems, so we're trying to predict curves rather than classes and rock types. But that is something that we are looking to bring in the next phase. So once we evaluate the performance, we can then select the best model, and then we can carry that forward to our modeling process. So jump forward to pretty much the start of this month, where we released update 3 for IP 2025, and we've now made the module multi-well aware, so we can bring in multiple wells from our project, and that allows us to get a wider pool of data to make more reliable and more robust models. And we also have powerful interactive data visualizations that allow us to filter the data, allow us to explore the different results in various visualizations, such as cross plots, histograms, and interactive log plots. And this goes beyond just looking at simple metrics. If we just focused on the metrics like R squared, we may end up being pulled the wrong way in terms of what is the best performing model. Whereas if we start looking at cross plots and if we look at log plots, we can actually see how well that prediction is actually doing. And it might have been a few outliers that may be pulling that metric one direction or another. And as you can imagine, when we start to feed in multiple wells, we start to slow down in terms of the processing, but we've done some big speed improvements via multi-threading, and that allows us to process tens of thousands of data rows within a few minutes or less. But obviously, as you add, say, if you added 100 wells, then yes, the time will get slower because it's a large amount of data, but generally the speed is much better than even the single well version that we had previously. And finally, we've improved the Experienced Eye feature selection algorithm, which is one of the feature selection methods, and that just helps us get some better results, and that obviously carries through into the prediction models. What I'll do is I'll jump over to IP to just give a brief live demo, and we can see it in action. So here we are with an IP. I've already got the inputs set up just to save a little bit of time on this webinar, but adding inputs into this module is fairly easy, as we'll see in a second. So this module is in the machine learning menu under Experienced Eye, and it's here that we can then launch straight into this module. So it's in the same place, I think, in IP 23 and 24. So once you launch that module, you then are presented with a multi-well grid. So previously you had a single well, basically a single well grid where you just selected the input curves and then ran the module. Here we've got the full grid that if you've used any of the curve prediction modules before in IP, then you'll be familiar with this sort of layout. So here we've got 3 wells from the vol field, which is a good open source data set that's out there. And we're trying to predict acoustic shear, and we're using a variety of input curves. And here we've got bit size, gamma ray, neutron, PEF, deep resistivity, caliper, compressional, and medium resistivity. So we can easily feed these all in. If, however, we ended up with a well such as 19 here, and we didn't have these input curves, it's automatically flagged for you that we don't have curves within this particular well. So what that means is we can't use that well in the model and we would have to take it out. But then you can go and select an additional curve from the drop down, wherever it may be, and then add it in and it will suddenly go white, which means that we can use it. So through some of the curve aliasing within IP, we're able to pick up curves automatically if they've been set up correctly or if they've got very similar names. So it's fairly simple that way. So I'll remove that well out of the process. And if we wanted to add in more wells, it's just a case of clicking on the last column and then it'll populate the grid with an additional column. Once you've got the wells in, it's then a case of selecting the interval that you want to use. So in this case, I'm just going to get the depths from zones and I will pick that up from the formations zone set. And we'll go from Ekofisk down to the Skagerrak formation at the bottom, and we'll select that for all wells. So any wells that don't have a formation top or don't have those formations, then it will default to the top interval for that well rather than a shorter interval. So one other thing that we've introduced, which is a big thing for training and testing of our models, is the ability to choose whether we want to do an automatic split, which is basically just using a random point selection throughout our entire data set, or whether we want to use wells for training or for testing. So if we've got, I don't know, say 10 wells within our project, and we maybe want to train them by area, so maybe we've got some wells on the outer edges that we want to use for training, and we want to try and predict on some wells that may be nearby or slightly in from those wells towards the center of the field project, then we can split the wells out that way, or do it through, say we've got 5 key wells within the project, then we want to maybe use them for training and then select a few more wells for testing. So there's flexibility there to allow you to choose whether you want to use certain wells for training, testing, or to take an automatic ratio, which is generally 70-30. Sort of the default value for that, but that number will vary depending on the size of your data. If you've got a smaller data set, then you generally want to go with a slightly different ratio of, say, 80-20 or 90-10. So once we've got that all set up, it's then a case of just going to the outputs. So this module only outputs the two curves at present, which is one is whether a row qualifies, and the second curve is whether the row or the data row has been selected for training or testing. And that's the two flags that are output, and they can be visualized on a log plot. And then we've got a series of options for our model. So we've got the ability to identify duplicate curves, which is done through or duplicate or very closely related curves. And that's done using the Pearson's correlation cutoff. So if we've got a curve that's very closely related to another, but not quite, and the example I like to use is where we've got, say, 2 porosity curves, we've got a porosity in decimal and a porosity in percentage, then those 2 values, if we did a straight comparison, would flag up as 2 different curves because they're different ranges. But if we plotted them on the same scale or on top of each other in a log plot, we would find that they're exactly the same. So we can use the Pearson's correlation cutoff to try to exclude highly positively correlated curves from the model. And the next option down is where we start to specify the training percentage. So by default, it is set to 70, but you can come in and change that. And you can see that 20% will be used for the testing subset. Put that back to 70. And then we've got the choice of feature selection methods. So we've got our unique and proprietary experienced eye feature selection, which is a derivative of domain transfer analysis, which is a unique model to IP. And we've also got Pearson's correlation, backward feature elimination, or I believe it's also recursive feature elimination, just different terminologies. And these work in different ways. So Pearson's is a straight filter method. So we're filtering out lower values from the Pearson's correlation, whereas backward feature elimination is doing a little bit more behind the scenes with, say, a multilinear regression, and it's looking at the p-value or the probability value of the results of each of the features in comparison to the target feature. And then we can remove some of the values that are that have a higher significance level, so the ones that don't really relate well to the target feature. And we also have the user-defined orders that I mentioned earlier. So if you come back to the input grid and say you want to move these around, you would select the curve in the default name column and then move it up or down. And then you can see how well your say technical knowledge compares with the automated methods. You can then see how, say, maybe you prefer gamma ray, neutron, and PEF at the top, and then you can see how that affects the results. And then finally, we've got the prediction models that we're going to run. So at the moment, we've got our three curve prediction models, so domain transfer analysis, multilinear regression, and neural network. And these will be run in the background for all the different combinations of inputs. So what I'll do is I'll quickly run this. This should hopefully run very quickly. Tested it just about an hour ago. So behind the scenes, what it's doing is it's running the feature selection process, but it's also doing the data quality checks behind the scenes. So it's trying to look for whether we've got monotonically increasing curves or whether we have straight curves and whether we have missing values within our rows. So then it will drop out a row if there's a missing value in one of the curves. So as you can see here, we're processing 60 different combinations of models, and it's going much faster as it's using up all the threads available on the computer. And then once it's done, we will then jump into the results tab. So before we jump into the results tab, if you want to see a summary of what's actually been done, you can come into the data summary tab, and this gives you an idea of what the training ratio was, what curves were dropped out. Here we've dropped bit size out because obviously it's a fixed value curve, and we just want to remove that. And then we can see which curves have been selected, and this is just handy to copy and paste into a report so that you've got full transparency of what curves were used, what ones were dropped, and it keeps that traceability. So if we come on to the results tab, this is split into different panels compared to the previous module or the previous version of this module. So we've still got the feature selection results at the top. We can see that we're predicting our acoustic shear, and we can see the rankings for the different methods. So we've got experienced eye feature selection, Pearson's correlation, which is the absolute score. So Pearson's correlation, as I mentioned, can go from -1 to +1. So we've just taken the absolute value as part of that ranking rather than having to deal with negative numbers in here. Then we've got backward feature elimination, and then we've got a user ranking as well. So that's tied to how we set up the input grid, and you'll see that the BS curve, the bit size curve, has been dropped from this process. So we've only got 7 input curves that are being compared. The next section down is the prediction model performance, and this is all of our metrics for all of the wells that we've selected. So this is an aggregation of the metrics. So the way to illustrate that is if we have a look in the top right, we've got the displayed wells, So we've got F4, 14, and 1A. And we can untick some of these, and then we can see that we've got the results for that particular well. And the easiest way to see that is within, say, a box plot here, which I'll come on to in a bit more detail. But with this grid, these are the results for F4. If we wanted to see F14, we can then switch to the different wells and see the results. But when we combine all three together, we are aggregating those results, and they are calculated on the fly behind the scenes with the actual versus predicted curve, and we get those metrics from it. So it's not just R squared, as sometimes that can be misleading. We can also view the mean absolute error, which is basically a straight average between the predicted curve and the actual curve. And then we've also got root mean square error, which if we've got outliers within our prediction, then these get flagged up and weighted more, as it's just taking the square of the error. And we can view each of these different metrics to have a full understanding of how well our model is performing. And we can switch between training data set and the testing data set. So we do make a prediction back onto the training data set to allow us to look at the metrics and the results from the training data, as well as the testing data, which is the main one we want to see. So in the bottom, what we've got is the metrics range per well. So when I said we're aggregating all these results, all of these tiny little X's on the plot is a single result from a single well, and that's a single metric. And we can understand or try to gain an understanding of how spread out each of these wells are. So F1A here is quite tight and has got pretty good performance, but with some models within the middle well here, F14, we can see that we've got slightly poor performance towards the bottom here using R squared. And that just helps us identify wells that may be problematic or wells that are going to be good for this particular model. And we can zoom in on these plots as well. So these are fully interactive. So you don't have to pop out an additional plot to bring in the interactivity. So that just helps you zoom in to each of these different boxes. And that comes into play when we see some of the other plots. So just going through the different plots, and this just allows us to visualize the differences in the prediction results. So we've got a prediction model comparison here. And this is for a specific model. So for DTA on the test data, we're looking at how well do each of these feature selection methods perform for the top three to the top 7 input curves. And we can see, is there any degradation in the model? Is there any improvement as we move along? So for example, this neural network one here, you can see there's a big degradation as we start to introduce more input curves into the model, whereas some are slightly improving and getting a better result towards the end. So this just allows us to see, are we feeding in too many curves, or do we have enough if we stick with 3 or 4 curves? And it just gives that overview there. And we can also see the feature selection comparison. So for backward feature elimination, how does it compare with DTA, MLR, and neural network? And then we can see that the neural network in this particular case is performing poorly as we start to add in more input curves, whereas the other two models are fairly stable across all ranges of inputs, with DTA improving slightly as we get to 5 curves. And then we can compare the training and the testing results. So what this chart allows us to do is identify, if I can find one, there we go. So this allows us to identify whether our training data is performing better than the testing data, or vice versa. So our testing data is giving better results, which could be an indication that there might be some problems there in the data, or that the model is needing tuned. Whereas, say, we've got the training data that's the training result is performing much better than the testing result, and that gives us an indication that the model is probably memorizing some patterns there within the training data compared to the test data. So we want to maybe be cautious when we work with that particular data set. And then we've got our single well plot. So this is an extension of what we had in the single well module, where we've got the scatter plot of predicted versus actual, and a histogram showing the distribution of each of the results. And these are fully interactive, so we can move around the chart, the different model combinations, and see how the models compare. So we've got the red points, which indicate the active well. So I can switch to a different well, and we can see in the background we've got the grey points, which are the remaining wells within the model. And this just allows us to see how each of the wells compare. And down the bottom, we've got a fully interactive log plot, or a limited log plot where we can zoom in and we can look at the points, and we can also detach this as well. So if we wanted to open this in a new window where we've got a linked window, say we've got, I run out of room on this small screen here, where if we've got a linked plot, I can go change my well, and we can see that the log plot will update with that. And it's the same with all the other charts. So this is really great if you've got a big screen or multiple screens and you want to view these in a little bit more detail, or if you want to lock them, so you can open a direct copy here with the cross plot. And if we change the well, you can see that that one does not update. So you can easily compare different ones and see how they are sort of in a bigger view. So these different charts just give you a different view of the data, and they go far beyond just looking at simple metrics, which can be misleading, but it's just a much more visual way to see how well your model's performing. For example, here in this upper interval, we're performing very well on the prediction, which is in orange, and their blue is the actual. But there's a few areas, say where my mouse is, where it's not performing well, or over here on the right around about 3,400, that there's a slight difference in model performance. And then we've got a multi-well log plot. So this is all of our wells displayed together, and I think there is a limit, or a visual limit of 15 or 20 wells, and that was just picked because as we start to add more and more wells in here, it can be very cramped. But if you want to view specific wells, we can untick and remove them, or add additional wells if you exceed that limit. And these again are fully interactive. You can zoom in, and you can also use the mouse to move up and down and view those different points. And finally, we've got the multi-well cross plot, which is used to see how all of the different wells compare with each other. And if we wanted to, we can highlight that in red for the active well, and we can change that again through the drop down on the right here. So these charts, as I say, take you beyond just simple metrics, and they're fully interactive in terms of what you can look at the points and see how your model is performing, and you can zoom in and scroll around it. So that's the main parts with the plots. And then over on the right, if we want to find the best model, we've got these blue text links here where we can go to the best model and then see how that performs, or the second best model. And then there's very little difference here, but there is a small difference. Or you can change the different metric and then view the top 1 to 3 there, which may be slightly different depending on the data that's used. But I think in this case, they're all the same. But there are some cases where R squared is different to the mean absolute error in the top 3 rankings, so you then have to view each of those. Once you have the final model selected, it's a case of right-clicking on that particular model. So here I've got multilinear regression with backward feature elimination. Open this selected model, and it will automatically populate the curve prediction model for you to then go in and add, say, an additional well. That once you've added it, You then untick the model build because you don't want to train on that new well, but you want to use these free wells here to then predict on additional wells, which is based on the model that you've chosen here. And then I think that's pretty much the key things really with the new features in the results tab. As you can see, it's quite powerful, and you can go beyond the metrics and get a full overview of how well the model's performing and how the different combinations of inputs influence the results. So what I'll do is I'll jump back to slides. So that sort of concludes the overview of the module and some of the new features that we've added. And as I mentioned, we've made it multi-well aware, which allows you to work within a project or multiple wells and build more reliable and robust models for your specific project. And it's also flexible, so you can select specific wells for training or testing, or combine them together, or use a random point selection. And the powerful interactive visualizations just make it easier to explore the results from the various feature selection and machine learning model combinations. And also the speed improvements that you just saw there. We did 60 different model combinations, and that was done within about a minute. But as I say, that can vary depending on the size of your data. So that concludes today's webinar. And if you would like to have a one-to-one demo of this or custom training around this module, then feel free to get in touch with us and we'll see what we can do.